Hello everyone. Today we discuss contest 18. Not many people solve this contest for some reason, I don't know. So that's it. So like just 5 people. Where is everybody? I don't know. But again, it's like solve all the problems. Last 2 problems probably a little bit too hard. We'll see. Again, we'll try to solve it by yourself. But overall, nice. Let's go discuss the problem. So again, I pre-recorded myself, so I will. So it turns out to be much easier to discuss problems when you don't need to write code online. It's hard to write code online and discuss at the same time. So I will save myself some energies to pre-solve it before. So let's go. So first problem is pretty straightforward. So you need you have some items. Each item is pointing to some another item, and you need to find a triangle in this structure. And you just doing it like you normally do. You just look and see. So you start from any point and see if there is a triangle or not. So you make 3 steps. Yeah. So you start from some point I, go to point f of I, then to point 2f of I, then you stop. So if you finish at the same point, then you have a triangle. Pretty straightforward. So yeah, I believe there are multiple ways to implement it. It's just the easiest way I know. So you just go from 1 to n and just make 3 steps out of this. I'm slowing down here because I'm looking if I can have a cycle of length less than 3. So theoretically you may have cycle of length 2, but it's not a problem. So if you have cycle of length 2, then you will have 2 jumps and then move at the same point, but the third jump will be out. So cycles of length less than 3, it doesn't matter. That's it. So that's the whole problem here. You see here in the middle, yeah, this part. I'm just making 3 jumps out of given point I and check if I finish in the same point as I started. It just means I have a triangle. That's it. That's problem A. Okay, hope everybody solved this problem pretty fast. So let's go to problem B. Problem B is interesting actually. So there are multiple problems like this. In this problem, you need to construct the permutation with given properties. Yeah. So there are multiple problems of the same type when you need to construct permutation with some specific properties. Properties differ from problem to problem. So here we have simple property. We look at the consecutive elements, and we need A times to be going up and B times going down. So basically, you want to go up several times and then going down several times. Yeah. So you want to construct something like this, or vice versa. Doesn't matter. Yeah. But you want this to be a permutation. So the way I'm doing it is just taking some big elements first. So I have increasing sequence of big elements, and then going down here and taking small elements. So here I have a decreasing sequence. So you have some increasing sequence and then some decreasing sequence. This number n. You increase up to n, then decrease from n. Again, multiple ways to do it. That's how I implemented this. And I'm just doing it using 2 for loops. So the first for loop will make the first increasing sequence. Second will make this decreasing sequence. That's it. That's the whole code of problem B. Again, multiple ways to do it. That's just the easiest way I found. Let's go to problem C. Problem C is actually complicated. So there is a long problem statement and some pretty complicated model is used in this problem. So you need to read the whole problem statement again, understand what's going on. The goal is actually pretty, again, that if you understand what's going on and try to play with it a little bit, it's quite easy. So you start in point 0, then you decide where you can go, to the left or to the right, go in this direction, and then move to the closest tree in this direction. So you move, if you decide to go in positive direction, then you move to the closest positive tree, then you reverse go back to the closest negative tree, then again closest positive tree, and so on. So you move something like this. So you start in point 0, and then you go here, then you go here, go here, go here, go here, and every time you visit one of the trees. So you closest tree here, closest tree here, closest tree. And then you move to infinity when you finishes. Now, when you look at this picture, it's kind of clear which trees you can actually visit. So you visit some trees in the negative side, some trees in the positive side. And the number of trees you visit in negative and positive side is roughly the same. So like here, I may visit like k trees here and k trees here. Yeah. Or I may visit one more tree. So I may have another tree here. I'm going to stop here and then go here to infinity. Oh, 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 oh. I go to infinity to the left. Yeah. So I will visit k plus 1 here. Yeah. So in both sides, so you may visit the same number of trees in the left and the right, or one more in one of the sides. So depending which side you choose to go first, you may visit one more tree in this side. Yeah. So again, intuitively, you kind of need to look at all the negative trees, all the positive trees. Yeah. So you look at all negative trees, all the positive trees, check which side has smaller number of trees. For example, if here you have only k trees, then in the left you have only k trees. In the right you can't visit more than k plus 1 trees. Yeah. So if you have more trees on this side, you can't visit them. So you can just read. And you visit only the closest to 0. So what I'm doing here, So I'm collecting all the positive trees in one array, all the negative trees in another array. Then I check which one is smaller. So I do it like this. So if I do not have two separate cases, I check which one is smaller and just swap them. So now I have positive always greater than negative. So I have more points on the positive side than I do in the negative side. Yeah, and yeah. Now I just have two loops. So in the first loop, I collect all available trees on the positive side. So I can collect up to show me. Okay, so if I have x trees here and y trees here, then from the right side I can connect no more than minimum of y and x plus 1. So this is the maximal amount of trees I can collect. Difference between pushback and in placeback is very easy. So when you when you call pushbacks, you create this object and then copy it. So in placeback basically creates and push it at the same time. Normally, so C++ suggests you to do it. If you can do in placeback, you do in placebacks. It's slightly faster. I believe C++ optimizer actually will convert it to the same code. So C++ optimizer sees that I don't change this value. So it probably will just optimize it. But in theory, in placeback will not like create the object and then copy it. Yeah. So in theory, it should be a little bit faster. Here I have some bug. Yes, I forgot to sort the arrays. And interestingly enough, it actually passes all the sample tests. So yeah. So for this example test, it doesn't matter what you're doing. Basically, you have the good result. It happens sometimes authors give you pretty bad examples, so any even incorrect algorithm will pass all the examples. Like here, I didn't sort the arrays, which is like crucial part of the solution, but still I pass all the examples. Happens. How you find bugs like this? You basically look how I did it. I just read the whole code and find where's the problem. Sometimes it works, sometimes it doesn't work. Let's go, problem D. In problem D, no, again, when you play a little bit, so what's happening in problem D? So what's happening in problem D? We have a set of buckets, and we fill them one by one. So we put objects in specific order. So we try to put objects as close to the middle as possible. And if there are two options, we pick the left one. That's what's said in the problem statement. So if you read this problem statement, that's what's written here. Again, so you will put like this. I put 1 here, then here, then here, then here, then 5, then 6, and so on. Yeah. If you have so this pattern will happen if you have even size of your bucket. So if m is even, if m is odd, it's slightly different. So let's say 5 buckets. So if I have 5, I have 6, I have 7 buckets. Yeah. Then middle is right here. So you start from this point, then 1. Then you put here, then here. Then you continue. You put left, then right. Yeah. But you start from the middle because you have one middle point. Yeah. So again, you play with the model explaining the problem statement and try to figure out what's going on. After you figure out what's going on, you just see that you have basically two options. When you have even size of the buckets, you have something like this. When you have odd size, something like this. And that's it. Then you just solve a problem for both these options. I usually do it separately. Sometimes you can generalize it somehow, but usually I just write two separate codes for odd and even cases, just to make sure that it works in both cases. Sometimes you don't copy the same code. Sometimes you just invent something which works in general case in both odd and even case. But if you see that odd and even case behave kind of differently, sometimes it makes sense to just write two separate codes, one for solving even case, one for solving odd case. Let's see. Let's speed up a little. Okay, not a little. See, let's speed up it twice. So yeah. So here I'm solving even case. So again, let me show you again. So in even case, I basically have objects in pairs. So I put left object and right object. Yeah. Here I put left object and right object, left object, right object. So here I'm making this loop of size m divided by 2. Yeah. And every time I pick two objects, one slightly to the left, one slightly to the right. Okay? If I have odd size here, then I put one object in the middle and then do this pairing. Yeah. That's it. Now I just output the result. That's it. So yes. You need to output the result. You need to output n objects. So you put not m object, you put n objects. But it's easy to see that this structure is actually periodical. So after I fill the first layer of objects, I put one object in each bucket. I will repeat that again. So then initially you have 0 objects in all buckets. So every time you pick bucket with minimal number of objects. Yeah. So you will put one object in each bucket. Yeah. Then you will do the same, putting the second object in each bucket, and it will have the same pattern. Yeah. So I just make one pattern of size m and then repeat it multiple times. See? That's why I have this modulo m here. That's it. That's problem D. Quite technical problem. So again, the start of the contest was quite technical. So I believe, yeah, that may cause some troubles solving this part, but problems itself are not that difficult. Yeah, so they maybe a little bit more code than usual, but overall nothing really that difficult. Now we go into problem E. Problem E actually involves a lot. So probably first of all, you have very scary picture in the problem statement. So it suggests that you have some physics involved. Physics is scary, especially for people who don't know physics that good. Again, if you study physics in school, probably you have some advantage, but not really. So all the required formulas are given to you in the problem statement. And actually, even if you know physics, sometimes it may be advantage, sometimes it may be disadvantage, because sometimes problem authors, they use their own simplified or even not incorrect physical laws. So you don't follow your knowledge of physics. You follow what's written in the problem statement. Yeah. So what's written here? So we have this is actually a real formula. So this is how the resistance working in electrical circuits. So we have resistors and we have basic resistor has just resistance of 1 ohm. Yeah, you see. And then you build a structure of this resistance, and you're allowed to do only 2 operations here. Okay, see? So in the first operation, you connect 2 resistors in sequence, so you have something, and you connect one more resistor, R0. R0 is just resistance of value 1. It's just to make the problem set more scary. Yeah. So R0 equal to 1. Yeah. But they put R0 here and R0 here just to make it scary. So this value is just 1. Nothing scary. And this value is just 1. Yeah. So what you're doing first? And the question is to build a system with resistance equal to given fraction. So you have fraction A divided by B here. And you need to build a system with given rational number. Yeah. Again, problem is about rational number. So what we're doing here, we try to see what's happening when we do these operations to this rational number. Yeah? So you have system, it has some rational resistance. So what will happen to this rational number if we apply both this operation? So if we apply first operation, I start from fraction A divided by B, I apply the operation, I have resistance A plus B divided by B. And if I apply second operation, again, you just write simple formula and see what's happening. So, okay, here I simplify it and simple. Yeah, you do something like this. So in the first case, you get fraction A plus B divided by B. In the second fraction, you get fraction A divided by A plus B. That's it. That's it. So you have 2 operations like this. So here I believe here I stopped thinking. So let me show you what you do next. What you do next. So again, if you have little bit experience in number theory algorithms like this, maybe you have flashbacks at this point already. But if you don't have flashbacks, let me show you what's happening. Why you have flashbacks when you see this formula is because very similar thing happens when you have Euclidean algorithm. Let's move backwards. Yeah. So you have, let's say you have A divided by B. You can go to A plus B and B. Yeah. So let's move backwards. So we finish at some point A plus B. So let's rewrite this A plus B as C. Yeah. So you have like C divided by B. Yeah. Then the previous fraction was, so this A is C minus B. So you have C minus B and B. Yeah. And if so, and the same for the second formula. So if you have A divided by C, then the previous formula was A and C minus A. Yeah. Okay, let's use D. So let's use many letters. I'm out now. Yeah. So when you go backwards from the last formula to the first formula, you just subtract one. So you have pair of numbers. Yeah, you see numbers C and B, and you go from this to the previous pair. We'll be just subtracting one number from another. For example, let's make some example. So imagine you know the last value will be some, I don't know, 7/5. Yeah. So what was the previous fraction? No, the previous fraction was how you can construct 7/5. Yeah. So in the previous fraction should be like 2/5. Yeah. Then I apply the first operation. See. So here is 2/5. So this will be 7. Now, how to construct the previous one? No, this 5 is greater than 2. So the previous operation was you have 2/3. Then you apply second operation, and you have. Then you go backwards. So you do 2, 3. Previous was 2/1, and previous was 1/1. Yeah. So that's how you construct 7/5. Yeah. So you just go backwards and see what's going on. And it's actually the same as, okay, let's keep this. It's actually the same operation happens when you do Euclidean algorithm. Yeah. So basically we need to calculate number of steps we do while doing this. And we can do it by just, again, calculate number of steps of the same operation. Okay, hope it's clear enough. Again, let me show it. So final idea. So imagine you have a fraction x over y. Let's use two more variables here, and let's say x is greater than y. So if x is greater than y, what I can do? I can subtract y multiple times from it. So the previous time was x minus y, then like x minus 2y, y, and so on. So at some point I have like x minus k multiplied by y divided by y. Something like this. So we do this until we have this value x minus k multiplied by y is less than y. And you just need to find value of k. Yeah. Now it's easy to see that value of k is just x divided by y. And this value is just remainder. This is just k model. Okay, if you're not comfortable with this formula, you maybe just need to spend more time solving problems involving some simple number theory, like greatest common divisor and stuff like this. Something about Euclidean algorithm. Just play with this algorithm a little bit so you're more familiar with what's happening here. Yeah. No, actually, even if you don't know the Euclidean algorithm, it should be possible to solve this problem, but it's just much harder. Yeah. So if you never saw the Euclidean algorithm, so then you probably don't have these flashbacks, so you don't see the patterns, and it's harder. But again, overall, you solve this problem like this: you look at the formulas given to you, see what operations they actually perform, and then try to see how do you construct final number from the initial number. Let me show you the final solution. The solution itself is very short. Yeah? So I'm starting with numbers a and b, and I will just apply these operations until I'm done. But basically, I will implement the Euclidean algorithm. It will just be okay. Okay, it will be strange implementation of Euclidean algorithm, but okay. Yeah, pretty strange implementation of Euclidean algorithm, but it works. I will maintain invariant that a is greater than b, and every time, okay, see, so a is greater than b always. Then I take this a divided by b is just number of operations I need to do until I swap this a and b. So I apply this number of operations, then calculate it, then just swap them. So it's just strange implementation of Euclidean algorithm. And here in the result, I calculate sum of all numbers I do in the process. That's it. That's the whole code basically. Okay, so that's the problem. Again, if you don't know the Euclidean algorithm, what you can do? You can just look at the operations you have, and try to basically go from the end and try to think how would you get this last fraction in my case. No, basically you have some objects, yeah, and you have some operations, and you think how did you get this last object? Yeah. In this case, it's always unique way to get this last object. Again, let me show you. So let's save some more time here. Again, what operations I have? I move from fraction AB to fraction A plus B over B, or to fraction A plus B. Yeah. So in this case, my numerator is greater than my denominator, and here it is less my denominator. So if you have fraction x over y, you just look which one is greater, x or y, and you know which operation actually happened. So if x is greater than y, then the previous operation was x minus y and y. Yeah. if x is greater than y. And if x was less than y, it means I applied this operation. Yeah. So the previous was x and y minus x. See. And then what you that's not yet it. So you after you understand how the process is working, you still need to count number of operations. Yeah. And here you do this division magic. Yeah. Again, not an easy problem at all. Not easy problem, but some people solved it. That's good. Let's go problem F. Well, problem F is I don't like problem F. It's good problem, but again, it's we have very technical contest today, I believe. So many problems involve some careful implementation, and if you do something slightly incorrect, you will have you will have a lot of troubles. So let's see. So what we have in problem F. So we start from yeah. So what you need first is to basically draw a picture. Pictures will always make things easier. So you look how this size changes while you're doing it. So first few days you eat some grains and then they back. So you eat some grains and then all of them goes back on in the next day. Yeah. So first few days nothing interesting happens. You eat something and then the next day they put them back. So it happens while you first m days. Yeah. While you're eating less than m grains. So if you eat less than m grains, then every day you just refill the whole barn. Yeah. So first few days something like this happens. Then you have different behavior. After first m days, you have different behavior because you refill not the whole grain. So you eat m plus 1 grains, then only m refills. Yeah, so you have minus 1. So when you have m plus 2, then you have only m refills. So you have 2 more grains. So it looks like the number of grains is decreased quadratically. So it was decreased like linearly, but here it's decreased like quadratically. Yeah. So you have different behavior of this function in these two regions. See? So first, during first m steps, we're looking at this point. Let me draw a better picture for you. So what we're doing, we look at this bottom point here. Yeah. So so we eat something, then refill, then eat, then refill, eat, refill. Yeah. So, and we're looking at these bottom points. We need to find the first point, which is below 0, which is 0 or below. Yeah? And this point moves linearly. So here we have some linear function, see? But then after we eat more than m grains, we start having some quadratical function. So we just eat something and it refills not, then it eats something, it refills even less. Yeah. So after here you're starting to have some, okay, it doesn't look quadratic at all. So let me draw it a little bit more quadratic, something like this, and then you have here, okay, so it start to have a little bit more quadratic feeling. Okay, so here during the first m days you have some linear function, see, and here you have some quadratic function. It makes sense. This system has basically two phases. Yes, in the first phase, you eat less than m grains. Then you eat them, they refill, eat, refill, eat, refill, and then you eat more than m grains. When you eat more than m grains, then every time you eat more and more and more, but refill is the same. Yeah. So like the behavior of this function is different now. Yeah. Okay, so this is the first step. You need to understand how your function actually looks like. Yeah, and you see that you have two zones. You have zone when you have linear function, zone when you have quadratical function. Now, zone with linear function is easy to calculate. Yeah, you just need the first time when it's below 0. Easy enough. Quadratic zone. it's a little bit more hard to calculate. So to do it carefully, I just write all the function I need here. So I see if I during the day m+1, yeah, so during day m+1, I eat m+1 grains, yeah. So I decrease number of grains by m+1. Then m of them will be back next day, and in the next day I will eat m+2 grains. So I eat m+1, give m back, then get m+2. So the next day I will have m+3 grains eaten. Then I have m+6 grains eaten, yes, because +3, then +4, and so on. So again, if during the day m+x, so again, what I'm doing here, I'm trying to write some values of my function, and then from these values, I see how my quadratic function look like. Okay. Okay. Hope it's clear enough. So here you see it's here. I'm trying to interpolate my quadratic function. Okay? So I see during day m+x, I eat it m grains plus some sequence of the grains. So during first day, I decrease like number by 1, then by 2, but then by 3, and so on. So this is total decrease of the number of the grains eaten before. Yeah. So and I just write so this sum is sum of arithmetic progression. So it's x plus 1 divided by 2. So now I have this formula. You see. So this is number of grains I eat. So my total number of grains is decreased by this amount, and I need this amount to be at least n. So the barn is empty. Yeah. Okay, hope it's clear. It looks like sometimes it looks kind of magic. You just write some magic formula and eventually they work. Yeah? That's how I usually do. Or if you're good in math, you can just write good formulas from the beginning. So it usually doesn't work for me because I don't know if it's plus minus 1. You never know when you have plus 1, minus 1. So I just put some values and then make the formula which satisfies this value. So I know it should be some quadratic formula like this. Yeah? Now, from this formula, I will find the value of x. So the value of x will be minimal value which satisfies this equation. Now, from here, you have two options. You can solve this quadratic. So this is quadratic equation. You can solve quadratic equation, or you can do binary search. Both perfectly fine. So I will do binary search because I'm quite confident I can do binary search. It's much easier. So I know it will fit it in the time limit. I know it will have no problems with solving quadratic equation. You need to move to floating point numbers, calculate some square roots. I don't know to work with floating point numbers until I very have to. So in this problem, I don't have to work with floating point numbers. I can do it in integers using binary search. So that's what I will do here. Now see. So here first I'm take care of the special case when I have this linear function. It's easy. Yeah. So if m is greater than n, yeah, then I will stop just here. So during this linear function, eventually I will eat all the grains. It will happen in day n. Yeah. If not, then I'm taking care of this part. So I calculate this value as this value as d. Yeah. And I just need to find the minimal x which satisfies this equation. See? So that's it. So what I will do binary search. So here I'm doing binary search. I find the so I'm doing very carefully so I don't have integer overflows. So here I find the minimal r, which is greater or equal to this, and then I do the normal binary search. So I have how I usually write binary search. Again, I have the full lesson in code forces how to do binary search. That's exactly how I'm doing here. So I have two pointers. One pointers to something bad, one to something good. So in my case, L will be pointing to something bad, so L is not enough, but R is enough. Yeah. So for R, I have greater or equal. For L, I have less. Yeah. And I see if my middle value is greater or equal here, I move the right pointer. If not, I move the left pointer. So in the end, right pointer is the minimal pointer, which is good. That's it. That's problem F. kind of technical problem, I would say. So, but like you see, there's not that much code. So code is not very technical in this problem. But again, you need to write down all the formulas carefully. Don't make any mistakes. If you have plus minus one mistake, it's sometimes pretty hard to find actually. And yeah, so that's it. So you write down all the formula very carefully and try to take care of all cases you have. In my case, in this problem, I only have two cases, but you need to carefully take care of all of them. Yeah, and write down a formula and then think how you calculate this formula. In my case, I will just use binary search. In some another problem, you may use not binary search but just math calculations also happening. That's it. Okay, hope it's clear enough. This problem F. Now two problems left. Okay, problem G is okay. It was okay. It was kind of embarrassing for me, but you will see. But the solution itself is not that hard for problem G. Let me show you. I believe. No. So, how do you start with approach problem like this? First, again, it's a long problem statement with a lot of different variables. So what I'm doing first, I'm trying to just visualize what's happening. What's happening in this problem? You have n objects. Out of these n objects, you select some p objects. And then your opponent, look this chairperson, select some k objects. Yeah. So there are n objects in the beginning. I pick some p objects, and then he selects some k objects out of this p. So that's what's written here. Now I try to understand how do they pick the objects, and it's written here. It's written that they try to minimize value of sum of b on non-picked objects. So objects not in this set affect with value a. So all objects in this set give you a gray hairs. Yeah. So this is your basically penalty for picking this up. For picking this object is sum of all a in this k region. Yeah. Now in this region, which is not in this set, you have penalty this b is displacement, whatever it means, of these objects. Yeah. Now I see what I'm actually maximizing. So you maximize, yeah. So what they want to do? They want to minimize the sum of b and minimize sum of a. Yeah. So when I pick the set of k elements, yeah, I want to maximize sum of b inside this set. So if I maximize inside this set, I will minimize sum of outset. Yeah. So what my opponent is doing? They take k objects out of this given p object. So I select p objects, then they select k objects. See? Again, it's madness. It's a problem. I like it. And what they're doing, so they want to minimize sum of b in this region. To minimize this sum, they want to maximize sum of b in this region. Yeah? So I'm picking objects here in these k objects with maximal sum of b and then with minimal sum of a. Now, if you think about it a little bit, so imagine you have this auspicious problem. So you think how my opponent is doing. So they're doing like this. So they choose some objects. So they minimize this sum. So this is what they optimize. Yeah. So how would I do it? First, let's think about it. How would I do this? How would I maximize something like this? Maximize sum of something, minimize sum of something. You do it greedily. Yes, you do it greedily. So every time you pick an object with maximal value of b, if you have several objects with maximal sum of b, you pick with minimal value of a. So every time you pick objects with maximal b, and if you have several equal b, you pick with minimal a. Yeah. Now I think, okay, here you stop. You think, okay, I have some ordering of all elements. Yeah. So my opponent, when they will decide which k elements to pick, they always will do it in some specific order. So I have some ordering of all elements. Yeah. And in this ordering, my opponent will pick some, let's say, rightmost k element. So I pick some p elements. Now I have a problem like this. Now I have interesting problem. Now I have a problem like this. I pick some p objects. Yeah. And out of these p objects, my opponent will pick the rightmost k of them. Yeah. Because I sorted them in this specific order. So I sort my objects in increasing order of B and then in decreasing order of A. So my opponent will pick the rightmost K object. Yeah. And the question is to find the pick the P objects, so rightmost K of them have the maximal sum of A. I actually didn't read the last part. So you need to find objects with maximal sum of A. And also for the left part, you need to pick objects with maximal sum of B. This is something I forgot, but so I spend another a lot of time trying to understand why my solution is not working. But that's it. So again, so this is the problem. So I pick some P objects in such a way that if I pick K rightmost of them here, they have the maximal sum of A. No, and how you do it? No, again, it's easy. So imagine you know where you start. You know this position. So in this suffix, you just need to pick the objects with maximal value of A. Yeah. So the question like this: for every suffix, you want to find K objects with maximal sum of A. You can do it using any data structure. I will do it using set. So I will maintain set of all elements in the right sorted by the value of A. And I will pick the K maximum of them. You can use set, you can use priority queues, anything actually. Yeah. So first I will sort. Okay. So here's something strange. I normally don't use some structures. Okay. So for if I need structure of 3 integers, I would normally do it like this, just for simplicity. Not very good code style. Have pairs of pairs. But for 3 integers, it's usually good enough for a problem like this. So what I'm doing, I'm making these triples. I need this I because I need to output the indices in the end. So I need to keep the track of the indices, initial indices of all the elements. So this is the pair I want to sort. Yeah. So I want to sort by increasing of B and then by decreasing of A. So I make pair of B and minus A. Yeah. Here, see, I put B here minus A here. So then I will just sort. Yeah. And it will be sort by increasing of B and then by decreasing of A. Now we'll go from right to left and maintain the set of K maximal elements. Okay, how do you maintain set of K maximal elements? Every time you put new element in your set and then drop the minimal one. Yes, so I will maintain set of K maximal elements, and in this sum I will maintain the current sum of this element. So I insert one more element. Yeah, here, see. If I have more than K elements, then I drop one of them, minimal one. Yeah, so I drop minimal one, recalculate the sum. That's it. That's it. Now my set S contains maximal K elements, and this sum contains some of these K elements. That's it. Here I check that I have K elements, so I have at least K elements here. I believe you don't need to, but I just do. And here I check that I have at least P minus K elements in the left. So here I must have in this part at least P minus K elements. So I just check and update the result. Like here was a surprise for me. Okay, not a pleasant surprise. I need to output not the value itself, but the set of objects. Okay, it's kind of hard to implement in this program because see, I keep track on the sum and I calculate the rest as the maximal sum. Yeah, and now you need to restore the answer itself. So for this sum, you need to restore how do you construct this sum. This sum is actually written just in this set S. So this set S contains the element I need to pick. Yeah. The problem is I need to find the state of set S when I found this result. So what I'm doing instead here, I will just do all the thing once again. So here I found the optimal result, but I forgot what was the state of my set S when I did this. So what I will do here, I will just do it again, and when I see the sum of a given result, yeah, so I will think, okay, now I know the state of the set S, so I will just output everything from the set S. I believe it's not the only way you can do it. There are multiple ways to do it, I believe, but it's the easiest way I found. So first, again, sometimes you have problems when you need to restore the answer. So you need to optimize something and find the way how do you optimize this something. So sometimes it's easy to do it in 2 steps. First, you find the optimal result, and then for this optimal result, you find the way how you construct it. Yeah. So it's like in dynamic programming, you go from the end, you go backwards until you find the way how do you get this optimal result. In this problem, I just do it like this. So I have multiple intermediate states. Out of all intermediate states, I need to find the optimal. So I just do again all this process. And when I see this intermediate state which is optimal, I just stop here and output the current state. See? Okay, there are multiple bugs in this problem. Here I will do okay. That's incorrect. I will fix it later. So I need to output these items in the right part. So I don't have the picture. Yeah. So again, you select some p objects. Yeah. And then so some of these k objects has maximal sum of a. Yeah. But you need to output both all p objects. So you need to output these k objects and also these p minus k objects. Yeah. And what I didn't read in the problem statement, because I can't read, obviously, is that for these objects, you need to maximize sum of b. Yeah. And you do it just by picking the rightmost possible objects. So here we just pick objects because they are sorted in increasing size by b. Yeah. So maximal b is stored here. So that's what you need to do. And I in this implementation, I'm picking these objects because I can't read. Yeah. So I will fix it later. You'll see. That's it. Oh, here submit, have wrong answer, think a lot. Okay, spend too much time. Here I finally look at the see, yeah. So here I finally fix it. Okay, it took me like a lot of time to find this, and also yeah. So not my best performance today, but I'm actually quite impressed you solved this problem. So that's it. So let's look at your solution actually. Let's look at your solution. Very similar actually. Okay, so here you make the same. Yeah, but I see the same construction. Nice. You can use priority queue instead of sets. Why not? It will be slightly faster. Not a big difference, but yes. How do you construct the result? Something tricky is happening here. Okay. So you find the optimal position. Yes. Okay. So if you finally find a good prefix, then for the prefix you solve the problem again. Okay. Why not? Why not? So that's it. That's problem G. Very technical problem, and I would say I would did again. It's code itself is not that difficult, but there is a lot of code, and it's like you need to be very careful when you implement something like this. And the problem statement is long and so on. So a lot of small difficulties in this problem, which leads in something like this. But overall, it's a problem is approachable. It's just massive. Yes, there are multiple steps you need to make, and then you need to implement a lot of code, and then you need to find this. You need to restore the answer in the end. So many little difficulties in the end, leading with something massive like this. But I wouldn't say that difficult problem. It's just big in terms of what you need to do to solve this problem. But all the steps are not that difficult. Just a lot of them. Let's talk problem H. So in problem H, yeah. So what's written in problem H? You need to basically you have a graph, yeah, and you need to build as as many sequences of free edges like so. So I'll draw a better picture here. Okay, I'll draw a picture here. So basically you have graph. Okay, okay, it will not nice picture. Let me draw a better picture. So you have a graph and you need to split it into sequences of three like this. So sequence of two edges. So basically you need to make as many pairs of edges as you can. Yeah. So they not in every edge is belong to only single pair. Well, let me okay, so something like this. Let's boom, boom, boom. That's boring. Again, if you play a little bit with the model, you can see okay how they are doing. So I will let's okay let me use another one. So I will take for example this pair of edges, then let's say this pair of edges, and then this pair of edges, and then this pair, and then this pair. Yeah. And I think, wow, I actually used all the edges. I think, okay, is it possible to make an example when I cannot use all the edges? And when you play a little bit, you see you cannot. Okay, if there is odd number of edges in total, then one of the edges will be unused, obviously, yes? You use two edges, you cannot use this edge. So one of the edges will be not used. But if you have even number of edges, it looks like it's always possible to divide them into pairs like this. Okay, this is intuition. This is again, it's very intuitive. You just think it looks like it's always possible to divide them in pairs for some reason. Because I spent some time drawing these pictures, and it looks like it's always possible. Then you start thinking, okay, why it's true? What you can do, for example, you can think about some specific graphs. So when you have some problem about graphs, you may think about some special cases. For example, when you have sequence. So if my graph is just a chain, can I solve the problem? Look, yes, you can solve. For chain, it's easy. You just split them in pairs like this, and that's it. So okay, you think I can solve for this type of graphs. Let's do something more interesting. Let's do trees. So if I have a tree, is it possible to solve the problem when I have a tree? Let's move something here. And I think, oh, it's actually an interesting problem. So for the tree, you need to split all the edges into pairs. Yeah. So you can okay. For how to solve usually for the trees, you do it recursively from bottom to top. Yeah? So you go recursively here. You see this node. Let's see this node. It has like these 4 children. Yeah. If number of children is even, you can just divide them into pairs. So I have one pair. You have one pair here, another pair here, and that's it. So you used all the edges. Yeah? And the same here. If you have even number of children, you're just doing this. If you have odd number of children, that's more interesting. Like here, I have only one child. Okay, let's have 3 children. So if you have odd number of children, then you can make pair here, and then you have one child left. What can you do with this left child? No, it's kind of obvious. So you take this extra child and connect it with this parent here. Yeah. And you just repeat it from bottom to top. So here again, you have 3 children. So you connect this here, you connect this to the here again, you have 3 children, you connect this, you connect this. Finally, in the end, you may have one extra child of the root, which can be connected in because you have this. It just means you have odd number of edges. So in the end, you may have one edge left, only one, yeah, because it's happened only in the root. Yeah. So if you have one child, you're not the root, you just connect this like here. You connect this extra child to your parent. So you think, okay, I can solve problem for the trees. Now let's get back to the graph. And for this problem, it's actually okay, sometimes think like for the graph, it's actually problem is the same as for the tree. Because if you have a graph, let me show you. Every graph is a tree in some sense. Let me show you. So let's look at the graph like this. So you have a graph. You can what you can do. You can find any spanning tree. Let's find any spanning tree. For example, this spanning tree. Yep. Up. So you have spanning tree like this. Yeah. So you have spanning tree plus some extra edges. You can just connect these extra edges to your spanning tree. Yeah. So you take any end of this edge and connect it. For example, let's detach it from here. So I'll just make some virtual node here and detach it from here. And this edge I will detach and let's say attach from here. And this edge I will detach, let's say, to here. Yeah. So basically you have spanning tree plus some extra edges. And you can attach these edges to like any end of this edge. And then you have a tree. Yeah. So you have all the same edges. See? Sometimes you have this virtual node, but it doesn't matter. Yeah. Okay. Hope it helps. So any graph can be considered as a tree in this sense. So if I can solve problem for the tree, I can solve it for the graph as well. So that's what I will do. I will find a minimal spanning tree, connect all the edges here, and solve the problem for this tree recursively, like I did before. To construct this spanning tree, I will do simple DFS. So I will construct DFS tree. Yeah. How will you do it usually normally? So you build a DFS tree. Let me show you. So this is my DFS tree. So DFS tree has edges, 3 edges, plus some edges connecting answers to the descendants like this. So I have edges like this plus some edges like this. Yeah. So what I will do, I will connect these edges to the bottom edge. It doesn't matter that. So I will connect this to here. So every node will. So okay, let me show it like this. Let's do it like this. So this node will have children like children in the DFS tree plus all the edges which going up. So I'll have 3 children here plus 1 more child here. So I have 4 children basically. See? And then I will solve the problem using the same recursive approach. Okay, hope it's clear enough. Let me show you. Yeah, so here I'm drawing the same picture basically. So I see how is the problem for the tree. And then I start coding. How I code it, like I normally do. Basically, here this the simple how I construct my graph. That's how I call DFS. So I usually use this vector of vectors for my graph. This array z as the marking. So I will mark nodes if they are visited or not. And here I see I need to check if node is below or above or below. So I basically do the same as you do when you find cycles in the graph. Yeah. So I do 2 types of markings. I mark them 1 in the beginning of the DFS, 2 in the end of the DFS. Here, if I see 2, it means I have edge downwards, so I just skip it. If I have 1, I have edge upwards, so I add it to my C will be a vector of my children. So I have X, so I have all these children here. And if not, then I didn't visit this node before, so I need to call a DFS, and I will call DFS at the same time I will output the result. Yeah. So I call this DFS. See if I use this edge or not. I will return this bool. So this bool will tell me I need to add this edge to my set of children. So this DFS returns true if I didn't use this edge. Okay, so I need to remember the parents. See here. Okay, here I will just take pairs of children. So every time I take 2 children out of my list, see here. So I take 2 children out of my list and put them to the result. That's it. Now, in the end, I may end up with a single child or no children. So I will just consider both cases. If I have no children, I return true. It means I didn't use the age to my parent. And if I have one extra child, I connect it to my parent, you see? And then return false because I didn't, because I used this age to the parent, so it's not available anymore. That's it. I will just output the result. Boom, boom, boom. I also fixed the bug. Okay, here I see that I output too many triples. That's because okay, I problem test. Yeah, because I forgot to check here. I sometimes reuse the same age to my parent. Yeah, it's something you need to be careful about when you consider DFS like this. So one of these edges is actually the edge to your parent. So usually you trick it to something. You do something different with this edge to your parent, yeah, because you already considered this edge when you're going downward. That's it. That's problem H. So pretty nice graph problem actually. Pretty elegant solution. That's it. I believe that's all I can say about this problem H. So let's look at your solution also. Oh, you use disjoint. Okay, why not? Why use? Because you construct some minimal spanning tree, right? Okay. No, here you construct some spanning tree. Why not? Why not? It's also some recursive. So you're not doing it inside DFS. You do it out afterwards. Okay, so you're doing this DFS, just marking the parents and creating the order. No, okay, and then afterwards you're doing this. Okay, why not? Why not? Why not? So you see, if you have even if you have odd number of children, yeah, you just basically it's another way of thinking about it. Yeah. So you basically reverse some of the edges. So if you have odd number of outgoing edges, you take one of the edge and reverse it. That's another way to think about it. Yeah. Okay, it's a nice solution actually. Good, 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 good. So that's it. That's contest 18. Thank you for being with me today. See you next week.